Okay, good morning, everyone. I already have questions. Anybody have any more questions about those ideas? Okay, so we start. So I start with number 43. So here is the problem. We have the graph of y equal ln of x, y equal ln of x squared, and y equal ln of 8, and we have to rotate about the y-axis. Okay, so of course, as you know by now, I have to graph, and I know you probably, y equal ln, we all know how to graph it. It is not
I'm excited. Okay. Oh, I just hope that.
Okay, sorry, I have to mute. Okay, so ln of x, we know how to graph it. It's just go like this. That's the ln graph. And this is 1 in here. That's the ln of x. Now, ln of x squared, it looks kind of scary how to graph it. But if we think a little bit, we remember the property of ln is 2 times ln of x. So it's basically the same graph as ln, but you stretch it a little bit. So if x is 0, sorry, if x is 1, it is 1, and you stretch this graph a little bit. So this is the graph of 2ln. So we have, this is y equal to ln of x. And this one down here is y equal ln of x. So these are the graphs. And they also want us y equal ln of 8. So ln of 8 somewhere in here. And this is the region. So that's the region that I'm going to rotate. So those extras we don't really need. Remove them. And this is the region. Okay. Now I'm rotating this about the y-axis. So I'm going to take, we're going to fill this with washers, and the washers are going to be horizontal washers. So we're filling this whole region with horizontal washers. And this is my basic washer. It's right here, right there. So this is my yi. And this one is I am rotating, so that's my basic washer. So imagine this is going to be like that. Something like this. Okay, and I'm filling this whole region with those type of washer, one of the top of each other. All right, so this is here is my yi. It means from here to here, that's a y. And my question is to focus on a washer. All right, so typical washer. Actually, let me write it down here, down. Typical washer. All right. So since it's a washer, because we're not touching the axis of rotation, there is a big hole in here. That's why we know it's a washer. We need the outer radius. We need the inner radius. We need the little height, which make it a volume, and then the volume of a typical washer. Right, so now let us get started. So where is the inner radius from? This is my yi here. So I'm taking this little slice. My inner radius is from the axis of rotation all the way to the inner curve. This is the inner radius. All right, what do I need to do quickly to find the inner radius? I know what it is. What do I need to do?
Solve for y.
Exactly. I have to solve for
Is it for x?
For x, right. I have the y. The y is from here to here. Then this problem, I know my y. I want to find this horizontal distance. To find the horizontal distance, I need the x that correspond to this y. So let us see the inside curve. Y equal to ln of x. I need to solve for y. It means I divide by 2 both sides. It gives me the ln of x. I need to solve for x, so I take e to the ln equal e to the half y. It means x equal e half y. That's solving for x. So my inner radius is going to be this piece here, which is e 1/2 yi. So if I know, so that's the inner, means if I know y, I know the inner radius, e to the half y. Okay. Now the outer radius. The outer radius is, so this is my little piece I'm rotating. It's from axis of rotation till this piece right there, right there. That's my outer radius. And now I'm sure I have the yi. I need the x that corresponded to this y. So I need to solve this. But this is easy. We've done it before. So this will give me that x equal e to the y. Y is my variable in all this problem. So the outer radius is e to the yi. Okay. The height is my little delta y here. We have to be very careful. Y is my variable here. Okay. And now the volume is the area of the base times the height, which is make it into a volume. Without the delta y, it's just areas. We cannot add areas. We have to add volumes. So now this is pi times the outer radius square minus the inner radius square. I wrote something nonsense. Nobody corrected me. The inner radius is e to the half y. Okay, you correct me if I write something wrong. So that's e to the half y. Okay. So now the total volume is going to basically be approximated by the sum of those little volumes. So this is the height, and this is e to the yi squared. That's the outer radius minus the inner radius, e to the half yi. And I equal 1 to n. That's the idea, that I'm having a washer on the top of the washer, on the top of the washer, and I am adding the volume of those little washers. That's the picture that we're trying to get to. So now the total volume is the integral from 2. Always go back to the picture. To cover the region, I have to divide the integral between 0 and ln of y. Remember, y is my variable. So not ln of y, ln of 8. These are my limit. Now the inside is pi times dy e to the y square. And in a minute, of course, we make everything much simpler. I'm just making sure we understand every picture of it. And now the integration part. So this is, so to integrate, we have to simplify first, and then we proceed. E to the y square, it means e to the y times e to the y is e to the 2y. Remember, you multiply the power. Some students are still getting that a bit wrong. Minus e to the half y square. When we multiply the power, we get e to the y dy. And now we have to integrate. Okay, so it's equal to pi times. Now by now, everybody knows how to integrate e to the 2y. We have definitely to do a substitution. And if we do it, we get a half e to the 2y. that very soon I want you to memorize it because of how often we use this expression. Minus e to the y, the whole thing evaluated between 0 and ln of 8. Right, so finally, this will give me the following. Pi times a half e to the power 2 ln of 8 minus e to the ln of 8, that's at the upper limit, minus at the lower limit, half e to the 0 minus e to the 0. So finally, this is equal to pi times a half e to the ln of 8. Let us remember e to the 2 ln of 8. This is basically e to the ln of 8 squared. It means 8 squared, which is 64. And I do expect you to be able to do that. So it's going to be equal times 64 minus e to the ln of anything is anything, minus e to the 0 is 1. So I will have a half minus 1. So finally, I will have pi times 32 minus 8 minus plus a half. Okay, and the rest is nothing more than simple math. So that's pi times 32. You take 2 and you get here 24 plus a half. It means 49 over 2 pi. Questions about this problem? Okay. So let's look at number 51 and then we proceed. Uh, 51. They gave us the following graph, and they gave us the graph this time. So this is, I graph it because it's hard for us to do that. X equal to, so one graph is x equal to minus secant y, and x equal to y equal pi over 3, and y equal to 0. These are the boundary. Now x equal to minus 2 minus secant y, they totally gave us the graph because we actually don't know it. I don't, so I don't expect you to. And that's a 1 here. That's my pi over 3. And then x equal to 2. That's a 2 in here. X equal to 2 is this line. Y equal to 3 is this horizontal line. Y equal to 0 is this axis. So that's really the region they're talking about. And we are rotating, and that's important, rotate about x equal to 2. So my axis of rotation is parallel to the y-axis. Okay, so that's really my situation. So this is the region, and I am rotating it around the line x equal to 2. And the question is find the volume. So this curve here, this is x equal to minus secant y. So that's really this curve. Very good. So we're going to do exactly what we've been doing over and over. This is my y here. That's the y or yi, as I said. Whether you write y or yi, I don't really, it doesn't matter to me. So this is my y, so I'm going to take this piece here. And I'm going to rotate it about x equal to 2. Question number 1, rotate a horizontal slice. What do we get? because today we're going to introduce something else. So what do we get when we rotate this piece? So far we have two things. Is it a disc or a washer? What do we get in this scenario quickly? Disc. Because the piece is touching the axis of rotation. So just in your mind, you don't have to memorize any of this stuff, just rotate it. And you say, you know, we're going to get the honest to goodness disc. Since it's a disk, if I need to find the volume of this little disk, because this in this situation, I'm filling this with bunch of disks, and I'm finding the volume of those disks. That's really what I am doing. And I'm finding the volume of those each one of those disks, and I am adding them. That's really the scenario. For a disk, I need the radius. So typical disk. Disk, I don't need inner and outer. It's a disk. There is no inner. So I need the radius. I need the height of the disk, which is usually in this scenario. Today, something will change. And finally, I need the volume. Okay. All right, now back to you. What is the radius of the disk? I want every one of you to think about it. Even if you don't put it on chat, just you think about it. What's going to be the radius? And eventually, one of you have to put on the chat for me. I'll give you 30 seconds to think about it. All of you. First, you have to label it. Labeling is crucial, and I will ask you to label on your quizzes and exams, so you know what you're doing. What do I mean by label? What's the radius of the disk? The radius of the disk is from here all the way to here. That's what I mean by labeling. Two, you have to always to think, what's the variable here? What is the, so when I say what's the variable, it means which axis you have to, or which interval you have to split into pieces. We have to split the pieces on the interval on the y-axis. So y is my variable. So everything has to be in terms of y, which is given in here. So what's going to be the radius? Okay, the radius is from here to here. It's going to be 2 minus whatever this point is. But the problem actually gave me that. The problem told me that if this is y, this is the curve x equal to minus secant y. It means if you know the y, your x is 2 minus secant y. So the radius is going to be right value, always take away the left value. Right value, take away the left value. So it's going to be 2 minus, parentheses, 2 minus secant yi. The right, take away the left. So my radius is going to be here, 2 minus 2 minus secant yi. Now, of course, it's going to become secant. That's not the point, but the point is really the height is my little delta y. So it's this height of this little disk because we're talking about volume. So the volume is going to be pi times. Now, I hate keep dragging this. 2 minus 2 cancel each other out. Minus minus plus. This is secant yi. Okay, so the radius turned out to be fairly simple. Secant yi squared. That's the area of the base. And then you multiply it by delta y to talk about volume. Otherwise, I will be adding areas. We have to add volume. Delta y make it into a volume. So now the total volume is integral from 0 to pi over 3, because it's very clear, my interval of integration, of pi times the radius squared turned out to be secant y dy. And now it's just a matter of integrating this simple integral. So this is equal to pi integral from 0 to pi over 3 of secant square y dy. Okay, now let us remember. What's the antiderivative of secant square? Quickly. What's the antiderivative of secant
Tangent.
square? Tangent, exactly. That's the tangent y. Basic stuff that you have to know because those occurs a lot. Because derivative of tangent is secant squared. So finally, I get pi times tangent pi over 3 minus the tangent of 0. And this would give me equal to pi times tangent 0 is 0. Tangent pi over 3 is the sine of pi over 3, which is square root of 3 over 2, divided by the cosine, which is a half. So this would leave me with the square root of 3. So the answer is pi square root of 3. Okay. Any more questions about the homework? Because we're gonna move to the same concept, but a different approach. Good. Please do the homework or you're gonna be absolutely lost. Absolutely lost. All right, so now I'm going to put a problem in front of you and you have to tell me what is the problem with it. I mean, why the problem I will put in front of you is hard to solve. So here it is. So we're moving to section 6.4, which is, I think it's easier than this one. Okay. And it is volume by shells. Okay. So before we start this, let me give you this problem. So problem. So I'm going to take R to be the region in quadrant 1, which is bounded by, when I write B and D, I mean bounded. So you guys can use this abbreviation if you want. Bounded by the graph of y equal x cubed plus 2x squared, y equal to 3, x equal to 0. That's my region. We're going to rotate the region, rotate R about the y-axis. And the question is, find the volume of the solid obtained. Obtained. Okay. So this is my problem. I will graph because probably you don't, I mean, you should know how to graph this. You can use calculus 1 to graph it. You find the derivative, you find where it's increasing, decreasing, and all this stuff. And then we can graph this function. But now for the ease of the presentation, I will graph this. Since I'm only interested in the second quadrant, so I don't really have to worry about that. This is an x cube function, so it's gonna be looking somehow. It's not gonna have a wiggly thing. The graph is gonna look something like that eventually, but that's the piece I am interested in. Y equal to 3. That's y equal to 3. X equal to 0 is that. So this is my region, and I'm going to rotate this around the y-axis. And this point here, just by inspection, this is 3. What do you think this is going to be? Just by inspection. Because I definitely chose very easy number. What do you think this is going to be if you want the output to be 3? Absolutely 1. That's very easy in this case. And that's the region I'm going to rotate about the y-axis. Okay, so find it. I'll give you 30 seconds to think about it. I'll try to be quiet. Okay, anybody wants to comment? So we're rotating about the y-axis. Okay, so we're gonna take, at least that's the process we did before. We're gonna cover this. In this case, we're gonna be covering it with this because there are no holes. So what's the problem in this approach? What's the problem? What's the radius of the disk? Cannot take equation in terms of y. Exactly. The problem, absolutely correct, Arian, sorry. Absolutely correct. If this is yi and I want the radius, I need to solve for x in terms of y. It means I need to solve the following. I have x cubed plus 2x squared equal to y, and I need to solve for x. And as you know, this is hard. This is a cubic function. We don't know how to solve for x. So what is the issue here? This is hard because to find the radius, I write it clearly, because to find the radius, we need to solve for x in terms of y, which is hard. In terms of y, which is almost impossible in this case. Almost. Which is very hard. Close to impossible. All right, so that's really the issue here. So if I do follow the same idea that I did before, and I took this slice and rotated, I know the y, I need the x, which is impossible to get. So y as a variable in this particular problem is problematic. I cannot have y as a variable. So the only way I can have as a variable is have to be the x. All right, so this approach is this approach wouldn't work. Taking those slices actually fail. Y as a variable is failing in this problem. So I have to solve this problem again by taking x as the variable. Now, when I take x as the variable, what type of slices I will have to cover the region with? If I take x as the variable, it means I need to cover it with those type of slices. I cannot cover it with that anymore. And now that's the question. If I take, you don't have to write it. If I take those slices and we rotate them about the y-axis, we're not getting washers anymore because the washer, the height is very, very tiny. That's a washer. So we're not getting washer anymore. We're getting something very different. We're getting what we will be calling a cylindrical shell. Okay, so that's really my issue. This problem cannot be solved using the approach we did. So I cannot basically have y as the variable because the difficulty of solving for x in terms of y, I have to go back and use x as my variable. When I use x, I have to use those horizontal slices instead of the vertical slices. Horizontal will generate a whole different picture and the problem will be directly different. So that will be the content of what we will be doing today. Questions before I move on? Do you guys understand the difficulties of this situation? Yes or no? You're very quiet. All right. So let me note a little bit before, a small note that in the washer slash disk method, in the disk slash washer method, the slices we took, those little slices were always, so let's see, in the, when we rotated about the x-axis, when we rotate about the x-axis, those slices were like, those were the slices. When we rotate about the y-axis, and those generated vertical washers, and those form those vertical washers. So the slices were perpendicular to the axis of rotation. Okay, so this one gave me washer, this one gave me washer, and sometimes they give a disk. In this section, we will take slices. In this section, we will take slices parallel to the axis of rotation because of the difficulties we had of rotation. Okay, so let us watch a little bit. I don't want you to write for a second, but let me explain this. Suppose we have my axis of rotation is this one. That's my axis of rotation. And I take a little slice. So the slice have a certain thickness attached to it. That's really my slice. Okay. And I take the slice and rotate it about the y-axis. I want you to imagine in your mind as well what you're getting. I'm going to rotate it about the y-axis. So what is going to give me? So I take this and rotate it. I'm going to get this piece right here. That's what I'm going to get. And there is a certain thickness because this is here usually is the delta x. So the slice that I've rotated have a certain thickness attached to it. This is my slice. Okay. This is what we are going to call. So we're not going to get a washer. This is the washer. The height is very small. That's really a washer. That's very, very small. The height is not the delta x anymore in this situation. Absolutely not. So this is what we are going to call the cylindrical shell. So the picture is very different. So now the question is, what's the volume of a cylindrical shell? And then question number 2 is, how we're going to use this concept to find the volume. So cylindrical shell. Cylindrical shell. Okay. So I'm going to draw it exactly the same way I drew it a minute ago. At least try. So the cylindrical shell is this piece. That's the height of the shell from here to here. And the shell have a thickness. And you imagine you're rotating that. And I, on purpose, used the Sharpie to tell you that there is a thickness attached to it. And the same thing here. There. Okay, that's really a cylindrical shell. And the question is, what is the volume of the cylindrical shell? Okay, so it is, you guys imagine the shell is like this. If you take a cylinder where the boundary is a piece of foam that have a little bit of a thickness, a little bit of thickness, that's really what a shell is. Now, what's the volume of a shell? Right. How are we going to find the volume? I'm going to approximate the volume, not find the exact one. I'm going to approximate it a little bit. Take this shell and cut it, right? This. So imagine you have a cylinder, basically, and we are opening the cylinder. So by cutting it. So cut this a little bit. So cut here. And open. Cut and open. What are we going to get when we open this shell? Anybody can imagine the picture. So imagine you have a cylinder in front of you, but the shell of it with a little bit of shell at the boundary. You take the cylinder and you open it. What do you think you're going to get?
Semicircle.
No. Think about a cylinder in your head and open it. A can of pop. Take a can of pop. Open it. What do you get? Just take a can of pop. That's what I want. Open it. Cut it in one side and open it. What do you think you get? Rectangle. Yeah, you're actually going to get a rectangle, but not quite a rectangle with a certain thickness attached to it. So let us open this. We're going to get something like that. So this is the height. I'm going to keep it. And because the can, there is a certain thickness from here to here, we're going to call this the thickness. Imagine a piece of foam in the form of a cylinder. So there is a certain thickness attached to it. So this is the thickness attached to it. So we open it, we're going to get something like that. That's what we get. So rectangle, Rania is correct, but it's not, I'm not going to call it rectangle. That's a rectangular when I finish my sentence. It's a rectangle with it's a volume attached to it. That's called a rectangular prism. Okay, because it's a three-dimensional object where the thickness is very, very, very tiny. Now, that's a rectangular prism. What's the volume of this prism? What is the volume? If I forget about that and I give you a picture like this, what's the volume of this rectangular prism? The height times the length from here to here times the depth. That's exactly the volume. So let us figure out what are the dimensions of the prism in terms of the shell. So let us see in here. Suppose this is my shell. I'm going to call this the height of the shell. Remember, for the shell, the height is not small. From here to here, that's the thickness of the shell. This is going to be usually, that's the delta X or the delta Y in my problem. That's what's going to be the thickness. Now, then there is the radius. Now, the radius is, you can take the radius to be the inner or the outer. But this is the thing. Because the thickness is very, very small, too small, we're going to assume that the outer, the radius are very close in each other. So in this case, I'm going to write, instead of writing equal, I'm going to write approximately equal because I'm going to call R the radius of the shell. Whether you take it to the inner or the outer, they're going to be very small to each other. So instead of giving ourselves a headache, I'm going to approximate it. So now what's going to be the volume? When I open it, from here to here, this is going to be the height of the shell. So the height of this prism is the height of my shell. What is the length of my prism from here to here? Imagine you take in this, you open it, you plop it. So what's going to be from here to here? 2 pi, exactly. It's going to be exactly the circumference of this circle. So the length from here to here is going to be the circumference of the circle. It means 2 pi times the radius. So this is coming from the fact here that the circumference is the 2 pi r. And when you open it, the circumference is going to be the length of this rectangular prism. The depth of this prism that's the thickness. The depth is the thickness of the shell. Remember, the boundary of the shell is like a piece of foam. So there is a little bit of thickness attached to it. That will be my delta X and my delta Y. So the volume of a shell is going to be almost equal to 2 pi times the radius times the height. Remember, the height is not the delta X, delta Y for a shell. It's very different. Times the thickness, which make it into a volume. Otherwise, it's not a volume. Absolute memory, the same way we have to remember volume of a disk of a washer. I want you to remember the volume of a cylindrical shell. So the volume is 2 pi times the radius from here to here. It doesn't matter you take the inner or the outer radius. They are going to be very, very close to each other because the thickness is small. That's why I put approximate. I did not put equal. Times the height times the thickness. Okay. Now, sorry, we're going to go back to a problem and we're going to use this concept to be able to find the volume. And it's going to be very easy, as you will realize. And that's the only formula I want you to memorize in this section. So now let me set up the problem. and proceed. So this is the problem. Find the volume. Sorry, let me change pencil. Find the volume of the region obtained by find the volume of the solid obtained by rotating the region bounded by y equal f of x equal a, x equal to b about the y-axis. And we're going to use this new approach, what we will call the shell method. All right. So the idea here is as follows. I'm going to take a region. So suppose this is my function f. That's the graph. And this is A. This is B. That's the region. And the axis of rotation is the y-axis. Okay, so I move to the side and I rotate. I keep this for labeling everything. So I keep this and I rotate. So I rotate here. And I rotate that piece. So I'm going to have something like that. So that's the region I will get when I am rotating. All right. And now the idea is, instead of we're rotating about the y-axis, but I'm not taking those horizontal slices. I am really covering it with vertical slices. Okay. So the idea is, like we did before, I take this piece, I cut, you don't have to do that, and then I rotate every one of them. So the picture in my mind is as follows. We can stop for a second, tell you what the picture in my mind is. That's the picture in my mind. So we're going to take this region and we're going to cut it into pieces. I'm just going to use 3 for the clarity. And I'm going to rotate each one of them. So I rotate this, I get, and rotate that one. I'm going to get this cylindrical shell. And then I'm going to rotate that one. And I'm going to get another cylindrical shell. So I'm going to fill this whole region with cylindrical shell. And then I rotate this. And I'm going to get another cylindrical shell. So this would be the green one. That's my green cylindrical shell. And this would be my red. And this will be the pencil one. So it means I'm going to fill the region with those bunch of shells. And my last one is this one. That's my little, okay, this right here. And this is right here. And this is the region right there. Okay, so what I am doing is I am filling the whole region with shell. And I'm going to find the volume of this plus this plus this plus that. Okay, one picture to help you out. Do you guys think of an onion? I know it's not something pleasant to think about. You guys have seen onion, right? Cut the onion in the top. What do you see? You see a bunch of rings. The rings are what I'm thinking about as the cylindrical shell. So what you're basically filling the region with those rings of the onion. That's really a good picture. So these are the cylindrical shell is like a ring of an onion, and the onion is all filled with those cylindrical shell. So this helps you a little bit imagine what's happening. So now I have to compute the volume of each one of them and add them. And that's where the easy part is. So now I'm going to take my typical shell here. I'm going to call this xi if you want. You can call it this xi or this xi. It doesn't really matter. And this is going to be my delta x. And now I'm going to rotate this. I'm going to rotate it. So I'm going to use my Sharpie to rotate. So this is the rotation. Okay, I'm rotating, I'm getting this. So I'm filling that piece here. This is being filled with all those shells. That's the one that's being filled with a lot of shell. That's really what's happening. And now we're going to find the volume of the shell. So a typical shell. Okay, let's find the volume. All right. To find the volume of the shell, the three ingredients are radius, height, thickness. When I find this, I find the whole volume. So radius, height, thickness, volume. All right, step by step. What is the radius of the shell? Again, you look at the picture. This is the y-axis here. What is the radius of the shell? That's the axis of rotation right there. My shell is right here. X is my variable because I am basically cutting the interval on the x-axis. So what's going to be the radius of the shell? Okay, let me do the easy one. What's going to be the height of the shell? The height of the shell is from here up to here. So what's going to be the height? Quickly. F of xi. Absolutely. So the height, I have no issue with it. Remember, you're not going to memorize except the volume of a shell. So that's really where the thinking is happening. The height is the value of the function. Very good. What is the thickness of the shell? The thickness of the shell is my little delta x. Okay, my height is f of x. And now we're struggling with the radius of the shell. What is the radius of the shell? No, absolutely not. Sorry. All right. Uh, since you cannot figure it out, let me try the following idea and then, yes, let me try this and then uh, you don't have to write when I'm trying to explain something. Suppose I have a curve here, that's my function. And this is, let us say 2, and this is 4, all right? And let us assume, as I said, don't write, but I want you to understand. Let us assume when I split this into pieces, one of the pieces fell on 3. So suppose this is a 3 here, and this is my little shell. Okay, and I take this and I rotate it about, so this is my shell. I'm rotating about the y-axis. I'm rotating. Now I'm back to you. What is going to be the radius of the shell? All of you. Use this picture, not xi for the moment. That's going to be, the radius is obviously from here to here. So the radius is going to be 3. Are you with me or not? Okay. If I happen to my xi to be 3.5 right there, and I draw, of course, the radius is growing, and the radius is going to be 3.5. The radius from here all the way here. So in the general context, what's going to be the radius from the axis of rotation till the base of the shell, from here to here? This is going to be my xi, and that's going to be the radius of the shell. So the radius is xi. Okay, so you're taking this little slice, that's your little slice. How much you have from here to here? You have xi, and that's the radius of the shell. So the volume now is 2 pi times the radius times the height times the thickness. And the total volume is the sum of the volume of the little shells I equal 1 to n. Now, when the number of subdivision become very, very, very large, we cover the whole volume, 2 pi x f of x dx. Okay. So definitely, that's not the formula you remember. That's not the formula you memorize. You cannot memorize. The only formula you'll memorize is basically this one, and then you work with it exactly the same way I worked right there. Okay. So suppose I gave the following example. I'm gonna draw the graph. Very easy. Y equal root x. And let us say y equal x squared. The intersection point, I've done it several times, it's y. And I'm going to rotate about the y-axis using the shell method. So the shell method, it means I'm going to cover this with those slices which are parallel to the axis of rotation. And this is my xi. And I'm going to rotate this particular piece. I'm going to go all the way. This is what I am rotating, kind of. Okay. So now, tell me the radius, give me the height, the thickness, and the volume. And of course, we're going to label everything, and then we're done. All right, so this is my shell. The radius is from here all the way to here. That's the piece we're struggling with. That's the radius. It means from here to here. That's my radius. So it changes with xi. So it depends where my slice is. If my slice here, I have a larger radius. My slice here, I have even a larger radius. Here, the radius is small. Small gets larger and larger and larger. So the radius of the shell totally changes with where my slice is. So that's really going to be my radius, which is xi. What's going to be my height quickly? The height is this. What's the height of my shell? All of you. What's the height? Upper value minus the lower value. That's the height of the shell. Thickness, the delta x. Volume, 2 pi times the radius times the height times the thickness, which will make it into volume. And finally, the whole volume is integral from 0 to 1 of 2 pi x root x minus x squared dx. Okay, so of course I have to stop here. Please do your homework for tomorrow. This is not very hard, but you have to make sure you understand how we are filling this whole volume with like onion rings, if you want. That's to help you a little bit. So it's not, and the radius of every shell is absolutely changing with where my shell is. That's why it was not b minus a. The radius is, if I have a piece here, my radius is going to be smaller than the radius of the black piece, and so on and so forth. right? Okay, so that's it for today. Please do your homework. Please do your homework. There is no other way out. Any other question before I let you go? Is the x the radius in the equation? Absolutely. X is the radius. X is the radius. Crucial. So that's the radius. That's the radius. This is the height. That's how I read this integral. This is the height, and this is the thickness. That's how you read the problem. Radius, height, thickness. Any other questions? Okay, do your homework and have a good rest of the day. See you tomorrow. Remember, I have office hours, I think, today. So please show up on my office hours. Okay, bye-bye, guys.
Thank you, Professor Elias.
Thank you,
Sure.
Professor.